Good morning. Today I would like to give some additional elements of the work we have been doing on basically studying the dissipative properties of the climate system, and this work has mostly been done together with Salvatore Pascale in the University of Hamburg. And so let's see what we are going to tackle today. So basically, we will basically start again from some of the elements we have introduced in previous seminars. So somehow the idea is again to consider the interplay between structures and the turbulence that we observe in the climate system, and somehow the link we want to study, what we want to focus on, is to see how different scales of motion contribute to entropy production, and somehow measure irreversibility at various scales. And in this case, we literally mean spatial and temporal scales. And somehow the concept is that entropy production has to do with the dissipative processes at different scales, and maybe we can use some of these ideas to infer what happens at the scales we are not able to resolve. So that this is quite tentative yet. So again, this is a picture already shown, and I will in a second show a slightly updated one. This is the crucial point, and when we look at climate systems, we have variability of a vast range of temporal and spatial scales. We have also features that appear at specific scales, and we have processes that support somehow that we can derive even from linearized equation of motions that allow us to find these features in a simplified setting. I would say as like clear examples, if we go to small scales, we have convective instability that gives rise to things like thunderstorms. We have baroclinic instability, which is a much larger scale process in space and in time, gives rise to latitude cyclones. In between, we have fronts that can be explained by semi-geostrophic theory as an example. Okay, now this is a better graph describing again, this is related to the atmosphere, and describes again various kind of processes of interest for various disciplines and sub-disciplines of meteorology. And there are this nice classification: alpha, beta, gamma, microscale, mesoscale, macroscale, and so on. But it's more interesting to look at on the, I would say here on the right hand side, and we say that depending on the model we choose, so mesoscale or a microscale model in this case, some processes are directly simulated, and some are parametrized, and some appear as boundary values. So this is exactly the interplay between different scales of motion as they are realized in operational weather forecast and in research. So this is, let's say, the problem of connecting different scales is very crucial. We already mentioned that somehow this appears in this fact appears in data, appears in models, and appears in the point of view people taking in trying to understand the properties of the atmosphere. So somehow we can try to understand how things go, looking at concentrating on these features, concentrating in the energy transfer across scales, in turbulence, or trying to study waves and trying to study how waves, let's say, contribute to transport, to predictability. So these points of view are, let's say, complementary from my point of view, and none of them is sufficient, I would say. So, and 3 points. In fact, the atmosphere has indeed features like, say, tropical cyclones, but this is not, or these organized motions are just part of the story. Not everything happens through these organized features, and they have life cycles, but then we have to understand what generates them, how they are dissipated, and this takes place in the interaction with the background flow. Again, waves are not, we see waves because there is an instability process. Instability process that makes them grow, otherwise we would not see any neutral waves. So as an example, the useful concept of a neutral wave like a Rossby wave is a fiction we have, because if a wave were neutral, by dissipation it would disappear. So there is an instability that keeps, or a forcing that keeps it alive. So again, sometimes we move the point of view. Okay. Now I want to mention some other peculiarities that of the atmosphere that in fact we are trying to look at today. So Victor Starr in the 60s, 50s I think, and then in the 60s, somehow introduced, wrote also a book on a negative viscosity phenomena. So the thing that shocked the meteorologists of let's say the classical period of meteorology in the 50s is that once data became available, they discovered that in the region where there is the jet, fluxes bring, basically transport momentum towards the region where there is high momentum. So you have a convergence of momentum where momentum is high. So this implies automatically that a simple dissipative and diffusive theory of atmospheric processes doesn't work, because there are regions where this, in fact, does not happen. So that's how you have a negative viscosity in some sense. So of course this is thermodynamically very problematic. And much later, actually Michael McIntyre, I don't know if still, but surely was professor at Dump in Cambridge, clarified that this happens due to long-range correlations, which are due to traveling waves. So waves work, basically waves organize themselves in such a way to make this transfer of momentum from, let's say, from regions of momentum-depleted regions to momentum-rich regions, which is the jet. And this is the mechanism by which the jet stays in place. And of course the question is, this is the dynamic point of view, which is a very typical of the school of Michael McIntyre, how can this be sustained? So there must be something that allows this to happen. That's thermodynamics gives us an information. Okay, this is possible, but there must be something that drives this. It cannot happen like on its own. Okay, so as I said, the key way of looking at when we want to look at this problem, I think that the most efficient way is in fact really trying to discover the interplay between the presence of sustained gradients, between the presence of non-homogeneous forcings coming into the planet, and how this basically sets in the dynamics of the climate system. Now, here I want to just recapitulate a few formulas that somehow tell us how to at least approach the problem. So the first line is the Lorentz energy cycle, which says that the dissipation, which takes place through a huge variety of processes, can be written as is equal to the work, to something that is the work, which is the transformation of available potential into kinetic energy, and this can be written as an efficiency that we can compute times the input of energy, and this is equal to the so-called differential heating. So this is something which takes place on a very large scale, and this is something that takes place on a very small scale. So the Lorentz energy cycle is a flux of energy from very large to very small scales. So this is so that is basically it's a thermodynamic transformation which ends up in a dissipative process. Then this dissipation enters in when we estimate the irreversibility of the system. So what we can write is that the material entropy production of the system can be written as as a product of a so-called what one can define as a lower bound, a minimum compatible with the presence of a certain dissipation. So this would be something like the dissipation over the average temperature of the planet times a factor which is 1 plus an irreversibility factor. And this alpha measures how much the system, what is the excess of entropy production the system has. So a system which is somehow, as an example, which has a very strong mixing, will have a very high large value of alpha. A system with a weak mixing will have low values of alpha. Okay, now let's concentrate on the dissipation. In the previous presentation, I talked more about first line. Now we want to look a little more at the second line, but in a different, from a rather different point of view. So, as I said, this is the formula we get, just taking from the books of fluid dynamics on entropy production. So entropy production in a fluid has two contributions. One is dissipation of kinetic energy over temperature, which is the minimum I mentioned, and then there is the rest, which is the irreversible flux of heat across temperature gradient. So, okay. Now, so this is the direct way of computing the entropy production in a fluid. Now, it is possible to rework a bit the equation by combining energy, basically by combining the energy budget of the system and the entropy budget of the system. And this work has been done by various authors, but in particular by Richard Goody, who showed the following. So, if I write the balance, I write the budget of the entropy of, okay, in the case of the Earth, you can basically separate the entropy related, the entropy production related to change in the color of radiation and entropy production due to so-called material processes. It's not a very good term because everything is matter, but anyway, let's say non-radiative processes. And you can separate these two budgets. Now, if you look at the budget of matter, or if you want a non-radiation, and you assume a steady state, you get this expression. So you have two terms. One is the integral over the volume, of course, time average of the density of entropy production, which is the same I put before, just by doing an integration by part here. And then you have the other term where, look, the sign is opposite. I have the convergence of heating rates here over T. So these are the heating rates due to radiation. So this is here, there is the optics of the atmosphere, exclusively the optics of the atmosphere, and here there is exclusively the atmosphere as the atmosphere and the ocean as fluids which have certain fluxes. So the nice thing is that I am totally separating the driver, and we will see this as very important, and somehow the system which somehow has its own dynamics. So since this has to be equal to 0, and since this expression here is exactly this one we have here, so this is the material entropy production. This is the same at steady state. So we can basically compute the material entropy production in two ways. One is by looking at the mixing and turbulent diffusion of the fluid, which is this formula here, where we use this. And in practical terms, here we use literally the part of the codes where we describe turbulent processes. And then there is another way, which is called the indirect way, where we use exclusively the optical processes of the atmosphere. So I forget about the dynamics, and I can compute the entropy production by studying correlation of heating rates and temperature. Note that there is an opposite sign. Okay, so this is an exact equation. And you can use one or the other, and you can, there are some, that was part of the PhD work of Pascal and Reddy with Gregory and Taillet to show that this work, and Ammau to show that this in fact works very, very well.
Heat flux from down, where does it?
It enters in this. So you have turbulent, so you basically distinguish between a large-scale advection of temperature of moisture, and then you have turbulent fluxes, so diffusion of basically temperature, so sensible heat, and diffusion of diffusion of moisture, which becomes an effective latent heat, and this basically takes place evaporation and condensation. So here we have basically the chemistry and the physics of the system, in the of the fluid, and here we have exclusively the optical properties. Instead, this is literally the divergence of the Poynting vector, basically. That's it. So interestingly, we immediately see that if we are able to do some approximate description of the radiative processes in a planet, even if we don't know very well how the fluid works, we can already compute entropy production. So if we focus on radiation rather than on the fluid properties, we still get the same information. That's very important. Now, again, let's see. All of this is requires now to understand which are the drivers. So remember, the drivers in a planet, maybe it's one of the definition of what a planet is. The driver is the incoming stellar radiation. So that's a key element that we will try to look at today. That is, we want to distinguish these two things. We want to be able to, I mean, this is, I think, a very interesting conceptual useful equality, but it conveys very different information. So let's try whether we can learn something from here. And again, keep in mind, the driver is the differential heating in the vertical, because incoming energy is absorbed differently across the climate and on the north-south direction, because we have more intense radiation in the tropics than, of course, in high latitudes. Can this become we want to be able to distinguish these processes. So now, looking at this and this, we want immediately to try to have a concept of how these exchanges process take place. So of course, we are going to have immediately, because of differential heating in the up-down direction, we are going to have some mixing, and the processes that are responsible for this are radiation and especially its convection. Okay, and this is a very fast process. Then we have another process of equilibration, which is called, in particular, pyroclinic adjustment, and then we have north-south gradients are killed by slower processes, which basically which come from the presence of mid-latitude cyclones. This is, of course, a very rough picture, but this is the basic concept. So anyway, here it's convection, and here it's synoptic weather. Okay? Different, when I want to describe synoptic weather, I'm not able to resolve this explicitly, because this is much faster and much higher resolution. So I have to parameterize this. So immediately we see that as soon as I construct a model of the global climate, the most important process of mixing becomes something below my scale. So this is, to me, a fundamental problem, a very fundamental problem. We are putting, we have to deal with this, but we are already somehow neglecting, or at least unable to describe the dissipation in this direction. No, so what you can get from basically coupling this north-south and up-down is something like this. So you can construct from the indirect formula of entropy production with a simple scale analysis. In fact, you can separate the total entropy production between this part, so north-south transport, and the transport between surface and upper layer. So this is and you can it comes out of the equation by taking some simplifying assumption on characteristic temperatures, but this is not a very bad assumption, and in fact you can use this to study global climate models. So what is important here, this equation is a time averaged equation on two-dimensional fields of radiation. So this is radiation, it's net radiation at surface, net radiation at the top of the atmosphere, surface temperature, which can be taken as skin temperature of the emitted long-wave radiation, and emission temperature, which is just, again, the fourth square root of the long-wave radiation at the top of the atmosphere. So if you give me radiation just at the surface and the top of the atmosphere in the 2D, in on a spherical shell, I can give you to a very good accuracy the dissipative properties of my system, which instead would require a three-dimensional plus one-dimensional fields. So this is much easier. And what we learn, we immediately can do map of entropy production, and we immediately see that the most important contribution comes, guess what, from the tropics. And the tropics and the very strong convective motion in the tropics are exactly the dominating factor of irreversibility in our system. And this is a more or less objective, an objective evaluation of this. If we can separate the contribution to entropy production coming from vertical and horizontal motion, and we discover that the largest contribution comes from the vertical part. So, as a first approximation, entropy is produced by vertical mixing. And then, one order of magnitude below, there is the horizontal mixing. So, that's, I think, useful. In a warmer climate, that's something we are now trying to put down. I have increase in the entropy production due to vertical motion, because a warmer climate has stronger convection, and a decrease in the entropy production due to horizontal motion, because in a warmer climate, meridional temperature differences go down. So the climate becomes, the high latitude regions become relatively warmer. Okay. Now, let's do a step backward, because up to now, here we have looked either at very high resolution in time and space, or very low resolution in time and space, because here I have reduced the system to a two-dimensional system. So what lies in between? And what I argue is that what lies in between is extremely interesting, because I want to study how these different scales will impact the numbers I get. And I want to see if I can use this information somehow. So let's take now instead something much easier. And this has been let's say, has been the conjecture we had. So, I mean, if I take a very simple system, a continuum mechanics system, where I have Gonzaga relations. So I have a system, forced, whatever it has, and it has, I can construct the entropy production. This is a system with no advection, nothing. It's just basically, it can be a glass, it can be, I don't know, a solid or something like that. So if I have a simple Gonzaga relation, I have that temperature fluxes can be related to temperature, heat fluxes can be related to temperature gradients in a very simple way. You know, there is just basically I can construct a positive definite symmetric matrix that connect fluxes and gradients. That's it. So this is the entropy production, and I can write it in the following form. So Aij, psi I, psi j, and Aij is positive definite. And locally this is positive. So in each point this is a positive number. Globally it's positive because locally it's positive. Okay? Remember, that's already a point. This is positive locally, whereas the atmosphere, the entropy production locally can be negative, because as we have seen before, I can have negative with positive effect. So this is a different ballpark. This is a simpler system. Now let's use from this equation, let's apply Parseval's theorem and express everything. Instead of here you have time averages and the volume integrals, I just go into frequency wave number domain. So I can write the same term as a sum. It's actually a very trivial thing, as a sum of terms of this sort. Okay, and I get that it is an infinite. This term, this entropy production, is given by an infinite sum of terms, and each of these terms, labeled by the wave number and omega, each of these terms is positive. So each term coming from each, I can decompose my entropy production in pieces, contributing to entropy production at each time and space scale in a d omega dk. And each of these is also positive, and this comes from the very simple structure of my equation. So we know that the entropy production is not positive locally in time and space in the atmosphere, whereas it is in this simple system, but we have that in this simple system it is also positive locally in frequency and wave number. Now, we want to use this concept to look at entropy production in the climate for given spatial and temporal scale. Because what is the concept I am after? If I prove, I want to show that each temporal and spatial scale contributes positively to entropy production once I integrate globally. This is the concept of doing this expansion. Okay, so I can have here in this region at this time that I have negative entropy production, but all the processes on this scale of space and time, when I integrate everywhere and they take long-term averages, must give me a positive contribution. So a negative fluctuation must come at the expense of a bigger positive fluctuation. Now, what we do? So basically, looking from here, this is an infinite sum, and what is performing a coarse graining? Performing a coarse graining on these fields is nothing but doing a cutoff for the frequencies above certain value and the wave number above a certain shell. So doing a coarse graining is exactly cutting information in the previous. I mean, it's a way of doing coarse graining, of course. So now, if I do a cutoff, so I sum from 0 to an upper bound, my estimate will decrease. That is, the coarser the graining, the lower the value of the estimate of the entropy production, because I am neglecting positive terms. Can be small, but they will be positive. This is again in this system. But this is the analogy we wanted to bring forward. So if we find, in other terms, if I find, so in this case I know that the coarser the graining, the lower the value of the estimate of the entropy production, because I am neglecting the mixing occurring for a small time scale and small spatial scales. So this is mixing, so it has to give me a positive contribution. Now, this is exactly the case we have in the stratosphere, as an example. We have locally heat fluxes against temperature gradients. So not only we have negative viscosity phenomena, we have in the atmosphere also fluxes going in the wrong direction. So if you model fluxes, heavy fluxes in the stratosphere with a diffusion, it's not going to work, because in the stratosphere, fluxes can be in the wrong direction. Of course, what you have to conjecture is that there must be work done on this system to make this possible. There is no other way. There must be something that makes this possible, and there must be work. And if there is work done on the system, one can, this happens locally in space and time, what happens globally in space and time. Now, we know, in fact, that we have already proved, just by showing this picture and the other one I mentioned before, the negative viscosity, that the climate is not a diffusive, system, because otherwise you could not see this. And of course we know it is out of equilibrium. There are many phases, and that's why we have a very complex chemistry of the system. So, but now we can ask ourselves, what are our expectations on terms? We can construct the entropy production locally, space and time. You can repeat all the operations, the spectral remapping or something like that, and we can ask ourselves what we expect on the contributions coming from different spatial and temporal scales. Okay? And we have to keep in mind that the climate is extremely heterogeneous, vertical versus horizontal. So when we do the averaging, we have to be a little careful. Unfortunately or fortunately, the world is not just a cube, everything homogeneous, so things are different. But still, the concept we developed before, in fact, applies. Okay, and can we use this information to understand the relationship between forcing and dissipation, which is, of course, I think it's quite interesting. So now, let's see how we compute entropy production in a model, and there are various groups that are able to do this. There's nothing actually extraordinary. You just use the formulas I gave before, and you compute, you integrate over the volume the sum, you compute this correlation between temperature and heating rates, which come from different parts of the model. Can be the module of transport, can be the module of diffusion, of cloud formation, and so on. And the same here, look again with the sign reversed, when you look at the radiative budgets. So here you have just convergence of radiation. So we call this beta. And so this is entropy production with the direct and the indirect formula. So if remember, these two things are equal in this form. Now let's do coarse grain of the field. So this is, if I have my system at the highest resolution, I expect that these two quantities will be the same. Now I want to eat the humble pie, and I reduce, I have an output at my truth at highest possible resolution, and I reduce the quality of my data by doing spatial and or temporal averaging. So instead of having an output at, I don't know, 5 degrees times 4 degrees, I have an output, I generate an output at 10 degrees times 20 degrees, and instead of a resolution of 1 hour, I get daily output. This is normally done when we post-process climate data. Okay? If I don't have enough space, if I don't think high-resolution things are important. So what I do, in fact, is just performing an operation of averaging for a quantity phi of my climatic field. Now I define as a coarse-grained value of entropy production the estimate I get by, instead of using the original high-resolution data, I use this coarse-grained data. So that's simple. So I just degrade the quality of my information and I recompute this quantity. What do I get? First, let's look at time. So now I keep constant. I don't change the spatial resolution. I just consider temporally averaged fields. So I start to lose temporal correlation. What I obtain is that monotonically, by going from a time step to longer and longer averages. Okay, first we note that the direct and indirect formula in fact agree within, I mean, there is very small uncertainty that we know where it comes from at time step. When we increase the time resolution, we observe two things. First, the estimate goes down, and second, the estimate of entropy production decreases more for the indirect formula than for the direct formula. So at this point we were a little puzzled. I expected this to go down, but I didn't know why one is more than the other. So now, okay, let's do something different. I add averaging on time and averaging on horizontal surfaces. So I am basically taking a kernel, so at each level of my model, I average on a certain angle. Solid angle. So I instead of having information, I basically lose spatial resolution in the horizontal, but I keep the same vertical resolution. So I am basically getting coarser information, coarser geographical information in the horizontal. This is if I go along this direction. So this is okay. Here it's exactly the same graph I showed you before. Here it's I keep a highest possible time resolution, and I reduce my spatial resolution, and here I do both operation. And what I see is no matter if I increase my coarse graining, my estimate goes down. This is the direct formula, this is the indirect formula, but look, here we get, I don't know, 10, 12, here we get 5. So I get, again, the same qualitative properties. If I do coarse graining, I reduce my estimate, so I'm neglecting irreversible processes at certain scales. And second, which is still more puzzling, with this formula, the loss of information is worse than with this formula. It's systematically. And this is very robust, and is not, we have tried in various averaging, and it works the same. Now, let's do, instead of changing time and horizontal resolution, we change vertical and horizontal resolution. The time is not the most important. So now, what does it mean? If I go from here to here, I go from having very, high resolution information geographically to having one point in the globe, horizontally. So only averages on the spherical shell. And here I go from having 11 levels in the vertical to having one layer. Okay? So here my system is 0-dimensional. Here it's 3-dimensional, basically. Here it is 1-dimensional. And here it is 2-dimensional. Okay? That is what I'm doing. Let's see how this estimate changes. So if my system is reduced from 3-dimensional to 1-dimensional, so I'm keeping the vertical, I'm losing a lot of information on the horizontal, the amount of, this is, you see this 13, so I decrease my estimate of entropy production by about 10-20%. Okay? But if I kill my vertical dependence, I lose 95% of the signal. So this again is exactly what I showed you before, but now with continuity. So going from n levels to one level. And you see that this process is continuous. It's actually not very surprising. What you're doing is you have this system where you have this temperature profile and you have a very strong flux. Suddenly, you coarse grain it, you keep the same temperature, you reduce the temperature profile, you kill the fluxes, so the number goes down. It's actually nothing special, but we see that the big effect is on the vertical. Now look, I'm using the indirect formula. When I go to the system becomes 0-dimensional, the number I get is 0. Why? Because this is, when I'm here, I have reduced my climate system to a 0-dimensional system that reduces radiation and emits radiation. So it's a zero-dimensional system in equilibrium. It cannot do work. It cannot do anything. It cannot. So entropy production has to be 0. Okay. If I use the direct formula, remember in the direct formula I have the epsilon squared, the kinetic energy inside, where the kinetic energy doesn't care. So when I do all this process of reduction, instead of getting 0, I get a finite number. And this finite number I get, it is exactly the minimum amount of entropy production the system can have compatibly with its dissipation. So I lost every information on fluxes, but there is one thing that averaging cannot get rid of. This is dissipation of kinetic energy. So this stays. So with this procedure, I am able to recognize this minimum that I defined at the beginning. Okay, now using this procedure, we can systematically get back to the two simple models that to one, especially the two simple models I found before. So this is using the indirect formula. I can, looking at my equation, derive a simple model. Basically, this is in fact, it's a two-dimensional layer model of the atmosphere, which sees the climate. Sees the climate as something, a two-dimensional fluid, which mixes stuff. So if I can reduce the system to a two-dimensional fluid with diffusion, that's it, and I get a certain amount of entropy production. If I do the same with the direct formula, I still have diffusion, but I have also the dissipation of kinetic energy. So in other terms, I'm discovering that these two formulas, which are equivalent, if I take the highest possible resolution in space and time, they are totally non-equivalent when I do the coarse graining, because the coarse graining impacts in a different way these two terms, because I'm losing or gaining different amount of information. That is the key element. So we find, in fact, that the coarser the graining, the lower the estimated value of the entropy production, just like in a simple diffusive system. And of course, it means we lose information about transfer of energy across temperature gradients. And using the indirect method, which is about radiation, we can separate very well vertical and horizontal processes. Instead, if we use the direct method, even if we kill all the information, we retain the effect of the dissipation of kinetic energy. And this is the minimum we were looking at the beginning, because the system somehow maintains this information. Now, let's look again now at the difference between the values of the estimate of the entropy production at different levels of coarse graining obtained with the direct and indirect method. So here we are going from high to low resolution, high to low resolution. So here, this is the high resolution case. And in the high resolution case, the difference is 0, as we know. Now what happens that again, if we increase the coarse graining, the difference becomes larger and larger. So not only we lose information, but we always lose more information when we use the indirect formula. So this again, what we saw before is confirmed. And we want to understand why. Now let's compare, let's write again the formulas before. Delta is the difference between the actual value of entropy production and the value you obtained with the coarse grain data. In a linear approximation, which in this case is doing a simple expansion, you get that this delta, which is the decrease, has to do with the correlation between the coarse grained heating rates and temperature. The change in due to the coarse graining. Okay, so these are the fluctuations over scale tau and v. Okay, that is the crucial point for the direct and indirect. If we have this, this means that these correlations are stronger than this. It's very simple. So what does it mean? So remember, we find the change in the estimate of using the indirect formula is larger than the change of the estimate we get with the direct formula. So the correlations between heating rates and temperatures, the change in this, is larger here than here. But what is the interpretation? Now we get it. So the system is forced by the sun. It's not forced by someone steering. So of course the correlation between radiation and temperature field is stronger because this is the forcing. Okay, so this is the forcing. And this is the relaxation, literally. So what is, in fact, that's exactly the concept you have on a geophysical fluid. It is forced by radiation. It dissipates, okay, by its motion. So you release instabilities that mix. So this is the forcing and this is the dissipation. And guess what? The forcing is stronger than the dissipation. Otherwise, the system would never start to move. If the dissipation were perfectly strong, infinitely strong, it would immediately equilibrate, and I will not see anything happening. So obviously, these correlations are stronger than these other correlations. Now, of course, locally, in time and in space, so this means I have positive correlation. When I have heating, due to radiation, the temperature goes up on the average. This means when the temperature goes up, my fields will tend to cool. That's what it means. Again, this is exactly this is a forcing, this is a dissipation. It's a damping. Now, of course, locally in space and in time, I can have increase of temperature with convergence of heat due to material fluxes. I have advection, I have a latent heat release, and the atmosphere will warm up. But this happens at this time in this place. If I integrate globally, this term has to become negative. So that is the basic point. So the driver, this tells me that the driver at each time scale, spatial and time scale, is radiation, and at each spatial and time scale, the material fluxes dump this. Okay. So this is the picture that I think one takes out. Now, using the so what we have learned, first we have learned that this positive contribution to entropy production comes, in fact, from all time scales, spatial scales. which in some sense we have, I think, a very good, I mean, in some sense, I like this. It's a good concept in describing irreversible systems. I don't know much. I think, of course, this thing can be generalized. I don't know how. I mean, this is a very special and system, so there is no reason why it should work here. I think in any continuum mechanics system it should work. And using the various coarse graining, some extreme coarse graining, we are able to give numbers. So if the total entropy production of the Earth is about 51, 52 milliwatts per Kelvin per square meter, so we can separate it into 3 pieces. These are about numbers. 13 to the dissipation of kinetic energy, 6 to horizontal processes of diffusion, and 33 to vertical processes. And in a climate change, this goes up, this goes down. And this is maybe goes down a bit as well. So this is the kind of result we get. Okay. And of course, I would like to study this in other systems. So one is very simple. This is a full climate model. There is no, I mean, it's a full climate model. It's not really a simplified one. In a system where I have some sort of symmetries, like in an aquaplanet, where I can do better statistics, and these averaging make more sense, and then I'd like to do it in a Rayleigh-Benard convection and see what happens. I stop here. Thank you.
Yes, as far as I've understood, the difference you have between our two estimates, between the indirect and direct estimate of your entropy reduction, is associated with a coarse graining, the way you are coarse graining.
Yes.
Should we modify the way we are coarse graining in order to get
no
violation of this?
No, I think that no matter the coarse graining, you will get this inequality because this is how I physically see it. So because this inequality, in fact, given this equation here, this is the element. The coarse graining impacts differently because the two estimates, which are really accurately the same at high resolution, that's actually a very, very high precision result. I mean, precision for the climate, but it's very good because it means physically something different. So no matter the coarse graining, you will get that the second is larger than the first because the system is forced by radiation. That is the concept I tend to believe in. And of course, the problem of coarse graining says, then I have the scales below. So I cut off at my time step and my highest resolution of the model. What happens below? So one idea is that you could, when you do parametrization to describe the rest, you can try to incorporate some information on entropy production to pull down the cascade. And when you change the resolution, of course, this has been done with one resolution. I mean, a model, and I have with one resolution, and I have done coarse graining on the output. Part 2 is, which we have not done yet, it's quite annoying, is to take the model and change the resolution, run the model, get the estimate, and compare the estimates of entropy production of the coarse-grained model or of the coarse-grained data. That is a very different problem, and I think this can teach us something.
In the horizontal and vertical coarse graining, why did you put the horizontal vertical and the vertical horizontal?
You're right. It's I don't know why. I think because before we had done horizontal and time, and then we substituted with the vertical because the time is not as important. But you're right. Yes, it will make it a little easier to read. Yes, but yeah.
What is the real application in real climate science of this model?
What do you mean?
How it can be applied to global climate models? Why it's important?
It's important.
How it can be developed?
Depends what you mean by applied. Depends what the meaning of the word applied. But I mean, first you can different model. This is a way to if you change a model, you might want to study how the dissipative processes at different scales behave, and this is not easy to do. Okay, so in general, how different scales. This is a way to study in a global sense the behavior of scales of motion and the and the correlations between heating rates and temperature, which is the basic way the climate works. So you can expect that this will be relevant for certain properties of the circulation. You change a model, you change a parameterization, you change a forcing, and this will change. So you can study how climate change impacts properties at all scales. That's the first one. And you can study how different models behave. So this tells you how a model can, how two models represent differently. I mean, as always, when you look at global indicators, it's not going to give you one direct answer to phenomenology of a system. So why the Madden-Julian oscillation is right or wrong? Because these features are really small in a global scale in terms of contribution to energy, entropy, and so on. Another thing is that you can use this to develop a model of exoplanets where we have little information and we want at least to gauge some properties. Where energy budgets are not clear, entropy budgets are definitely not clear. People put different boundary conditions which impact this and change. So it's a way to see the structure of the dynamics. So,
yeah, I was a bit lost. So I mean, somehow you compute the entropy production using thermodynamical quantities. Can you compute the entropy production just directly from the mechanics?
From the.
I mean, if you have from the numerics. I mean, just on the microscopic level, somehow you look at phase volume expansion and something like that.
No, because here you have. The problem is that here you have macroscopic equation. You have to give me the rule to relate. You have a lot of parameters in between. So that's why I have to go to thermodynamics. If you give me the rule to relate contraction, the factor to relate contraction and entropy production, one could. I mean, one can think of doing it maybe in a simpler model. But I mean, when you start to get phase transition, this is extremely immense. Anyway, this is the thermodynamics works. Where it's a
you could do it in toy models. I mean, where you have somehow real mechanical model and you try to do a similar scheme. I mean, it has nothing to do in general with climate.
No. This method, yes.
Of course, graining and.
But the interesting is that you want to have a continuum system. So if you, with a continuum system where I can do a good formulation of it, might be something where I study it conduction or something like that, I could try this. So because this is not a cross graining in phase space, this is a cross graining in physical space. So that's very different. So yeah, you're right. I mean, in that case, it could be more interesting. It could be differently interesting. Let's put it this way.
All right, very much for this talk.
Thanks.